Hello, my name is Mohammed Bazik. So today I'll be presenting the diabetic retinopathy diagnostic system. So our group member consists of 5 members: Ahmad Mujahid, Muhammad Bazik, me, Muhammad Shafiq Zani, Muhammad Wafi bin Yusli, and Muhammad Haidar Azra bin Muhammad. So let's go to introduction. So what is DR? DR is a diabetic retinopathy. It is a diabetes-related eye disease that damages the retinal blood vessel. If it left untreated, it can lead to permanent vision loss or even blindness. So early screening is really needed to help to detect the DR at early stages to prevent disease propagation. So automated retinal image analysis is improved screening by assisting disease classification. This project applies traditional image processing and machine learning techniques to classify DR severity. So move to the problem segment. So the first one is manual examination of large number of retinal image requires significant time and effort. Retinal image often differ in brightness, contrast, lesion size, and overall image quality. Raw image may contain noise and irrelevant background information, reducing classification accuracy. An effective pre-processing and feature extraction process is needed before classification. The challenge is to accurately classify 5 diabetic retinopathy severity stage using traditional machine learning. So this is our objective. The first one is to pre-process retinal fundus image using green channel extraction, Clahy contrast enhancement, and media filtering to segment candidate retinal region using auxiliary sodium fluoride by morphological refinement to extract 10 traditional features from geometry, intensity, and texture domain to classify the extracted features using KNN and SVM to evaluate both classifier using confusion matrices, accuracy, precision, and recall. So this is our dataset. We source from the Kegel diabetic retinopathy balanced dataset. The dataset consists of 5 severity classes of diabetic retinopathy. Images were divided into training and testing set for model development and evaluation. MATLAB automatically assign label based on the folder name using image data store.
My name is Ahmad Mujahid bin Idris. Now I would like to present about pre-processing and segmentation. So this is the original image that we use for our project. So MATLAB reads each image using the IMReads function. So the original image serves as the input before pre-processing and feature extraction. After loading the original retinal image, we extract the green channel from the RGB image. The red channel has lower contrast, while the blue channel contains more noise. By using the green channel, important retinal features become more visible, making the following pre-processing and feature extraction steps more effective. This is Clahy contrast enhancement. After extracting the green channel, we apply contrast limited adaptive histogram equalization or Clahy. So this enhances local image regions instead of the entire image. It also makes blood vessels and lesions more visible and prevent excessive noise amplification. So this can produce a clearer image for the next pre-processing stage. After enhancing the image contrast, we apply a 3 by 3 median filter to reduce unwanted noise. Unlike an average filter, the median filter removes isolated noise while preserving the edges of important retinal structures such as blood vessels and lesions. This results in a clearer image and improve the accuracy of the segmentation process.
Okay, I'm Wafi bin Yusli, and next I'm going to present about the next process, which is contrast inversion. So contrast inversion is going to invert the filter image using the MATLABs in complement function to change the dark retinal structure to brighter regions and make the abnormal retinal features easier to detect. The next process is also thresholding. So also thresholding will automatically determine the optimal threshold value. It will convert the grayscale image into a binary image, and then it's going to separate the retinal features from the background. Going for the next process is morphological refinement. Morphological refinement is going to remove small noises and unwanted connected objects. In this process, it will refine and cleans the binary mask, and it will also preserve the important retinal lesion regions. Finally, in segmented region overlay, the refined binary mask is applied to the original retinal image. The background is removed, leaving only the segmented regions. And finally, the final image is then saved and used for feature extraction and further analysis. As you can see here, this is the segmented retinal image for 5 stages of diabetic retinopathy. The segmentation will highlight the important areas such as blood vessel and abnormalities, making the image easier to analyze and classify. And that's all for me. Thank you. I'm going to pass for the next present.
Hi, my name is Muhammad Shafiq Zani, and now I'm going to be talking about the feature extraction. The feature extraction transforms visual information into quantitative value that can be used as input for machine learning algorithm. 3 features domain were extracted in this project, including geometric feature, intensity feature, and texture feature. Geometric features are used to describe the shape and size of the segmented retinal lesions. The feature extracted from this domain including eccentricity that measures the elongation of the lesion, aspect ratio that is ratio of the lesion width of its height, and circularity that indicates how close the lesion is to a perfect circle. Next, the intensity features that describe the pixel value distribution within the segmented retinal region. The feature extracted from this domain including mean intensity, that is the average brightness of the segmented retinal region, variance intensity that measures the variation of pixel intensity values, and skewness intensity that measures the asymmetry of the intensity distribution. And lastly, the texture features. It describes the spatial relationship of neighboring pixels in the retinal image. These features were extracted using real level co-occurrence metric (GLCM) generated from the media filtered images. The features extracted from this domain including four features, that is the GLCM contrast, GLCM correlation, GLCM energy, and GLCM homogeneity. Then, all extracted features are combined into the feature matrix. Each matrix is represented by 10 numerical features and are stored in CSV format as shown in the slide. The feature matrix is used to train and test the KNN and SVM classifiers. The first classifier used in this project is K nearest neighbors or KNN. Hyperparameter K equal to 5 was selected for this project. It classifies a new image based on its 5 nearest neighbors. The predicted class is determined by the majority vote of the nearest neighbors. The KNN model was trained using the following MATLAB code that is shown in the slide. The second classifier used in this project is the support vector machine or SVM. It was used to find the optimal decision boundary to separate different classes. It used RBF, radial basis function kernel, to handle complex and non-linear data. MATLAB's error correcting output codes ECOC framework was used to classify the 5 diabetic retinopathy stages as shown in the slide.
Next is performance evaluation for K nearest neighbors KNN performance. Proliferative.dr achieved the best performance with a precision of 60% and a recall of 54%. Performance summary: overall accuracy is 40% with macro precision of 41.04% and macro recall of 40%. Next is support vector machine SVM performance, the confusion matrix produced by the SVM classifier. Among all classes, no DR achieved the highest recall at 68%, indicating that healthy retinal images were recognized effectively. So for performance summary, overall accuracy of 36% with macro precision of 36.46% and macro recall of 36%. Now we go to the comparison of KNN and SVM performance. Based on the evaluation metrics, KNN outperformed SVM in all three measures. KNN achieved an accuracy of 40% compared to 36% for SVM. Although SVM was effective in recognizing the no-DR class, its performance on the disease stage was generally lower. Therefore, KNN was selected as the better classifier for this diabetic retinopathy classification system. For conclusion, this project successfully developed a diabetic retinopathy classification system using traditional image processing and machine learning. KNN outperformed SVM, achieving the highest accuracy of 40%. So, in future work, we can focus more on improving pre-processing, feature extraction, and classification techniques. That's all from us. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Harun Azraf and I will present this demonstration of diabetic retinopathy diagnosis system. Step 1, load raw image. We choose the image from proliferative DR. Next, step 2, pre-process image. The image will appear here. Step 3, segment and refine. The segment is here and the refine is here. Step 4, extract features. The feature will appear here. Eccentricity, aspect ratio, circularity, intensity, variance, intensity skewness, GLCM contrast, GLCM correlation, GLCM energy, and the last one is GLCM homogeneity. Next, we diagnose the image. So the image will appear as stage 4 proliferative DR. Actually, ground here state that is not provided, but I will show you the result later. And the clinical finding, advanced diabetic retinopathy pattern detected, so that it's urgent. So we export the result to Excel, and it will send straight to the Excel, and it will show like this. The actual ground truth, as we say that it did not show here, it show here. Actual ground truth, proliferative DR, predictive proliferative DR, and it matched the status. That's all from me. Thank you.